Have you got a piece of paper ready?
Yep.
Okay. Can you draw phenyl rings? Just draw phenyl rings. 2 phenyl rings actually.
Okay.
Skeletal is fine. Just draw the skeletal.
Done.
Okay. And then make it phenol. Both of them phenol. Make it phenol.
Phenol. Yeah. Okay.
Cool. And then add a carboxylic acid group, CO2H, at position 2 for phenol number 1, and add a CO2H at position number 3 for phenol number 2.
Position 3, the meta position.
Yep.
Okay. Done.
Show me your diagram so that make sure that we're on the right track. Can you show? Yep. Cool. So the question is, which one is more acidic and why?
Which one is the more acidic one? There's 2 acidic groups, the phenol and the carboxylic acid, but then the carboxylic acid group is more stronger.
Yeah.
So,
like how can you tell the carboxylic acid group is a stronger acid than phenol?
carboxylic acid has 2 oxygen groups, electronegative groups, connected to the carbon.
Mm-hmm.
So the negative charge can be delocalized into those 2 oxygen groups.
So if I ask you to go into the lab, how can you show me that the carboxylic acid group is more acidic than the phenol? So that is your reasoning. But like if you had to go into the lab, and then you have one compound which has a carboxylic acid, one compound which is a phenol, how can you show that carboxylic acid is a stronger acid than phenol?
Carboxylic acids can react with sodium carbonate, but then phenols can't react with.
Yep, so it's not strongly acidic enough. Yeah, cool.
Yeah.
All right. So back to this question: which one is a stronger acid and why?
If I draw the ionized carboxylic acid groups on both of them, one of them, the oxygen anion, is closer to the OH than for the O12 position. The carboxylic acids group is next to the OH group, so that means it can form intramolecular hydrogen bonding, so it will be more stable. Deepax.
Do you mind showing me what you mean?
Yeah. Intramolecular hydrogen bonding.
Yep. Okay. So what about it then? So
it's much more stable and preferable over the other.
Show me again, please. So what you have drawn there is can you describe this to me? What is this interaction between?
The oxygen's lone pair forms hydrogen bonding with the oxygen here.
So okay, you can put a diagram down. You can put a diagram down. So just to go back on what you said the oxygen lone pair forms hydrogen bond with the oxygen.
Yeah.
What is a hydrogen bond?
Hydrogen bond. It's in electrostatic force of attraction between electronegative atom bonded to hydrogen. It's lone paired with another electronegative atom.
So you are saying that a hydrogen bond is between a lone pair on an atom bonded to hydrogen with another electronegative atom. That's what you said?
Yeah.
Okay. So a lone pair is rich in electron. Do you agree?
Yep.
So that's your delta minus, right?
Yeah.
So you're saying is the electrostatic force of attraction between that and another electronegative atom. That's what you said, right?
Yeah.
So another electronegative atom, what is the polarity on the another electronegative atom?
Also delta minus.
Hang on. So delta minus and delta minus, do they do electrostatic force of attraction?
No.
Eh? So what is this hydrogen bond you just said then? So it doesn't make sense at all because you have just contradicted every single thing you said. You started by saying force of attraction. Then you started saying lone pair, which is lone pair of electron, which is rich in electron, delta minus, because it carries the charge of the electron, with another electronegative atom, which is a delta minus. So delta minus doesn't attract delta minus. No such way is that electrostatic force attraction.
Yeah.
Idea. I mean, you contradict yourself. So what are you exactly trying to say? I mean,
Oops. It should be with the hydrogen.
oh, so that's what you mean now. Okay, cool. So basically, if you draw the OH bond as a display the OH bond, you will get a very nice six-member ring there. Well, like intermediate, a six-member stabilized intermediate due to the hydrogen bond, the intramolecular hydrogen bond between the oxygen lone pair that is on the carboxylate and the delta plus hydrogen, which is bonded to the highly electronegative atom. So now you have a full negative charge, which is rich in electron. You also have a delta plus hydrogen because very delta plus because it's bonded to highly electronegative oxygen. And now you have this electrostatic force attraction called hydrogen bond, intramolecular hydrogen bond. Okay, so what about it then? I say like that is not the original question. The original question is which one is the stronger acid. So
Since this one can form the intramolecular hydrogen bonding, it's a more favorable structure compared to the other one. So this one is the carboxylic acid in the ortho position is more stable. So it's more likely to lose hydrogen, H plus.
yep, cool. So acidity is to do with the stability of conjugate base, which you have just drawn the deprotonated form is what you call a conjugate base of an acid after you lose a proton, right? So
Yeah.
the more stable the conjugate base, if you can stabilize the conjugate base more by inductive effect, which is electron withdrawing effect, then you will make the negative charge slightly localized on that region. Is good. Inductive electron withdrawing is good because you are withdrawing it. But electron withdrawing by resonance is even better because resonance is a stronger electronic effect than just inductive effect. Obviously, in contrast, if you have an electron donating group, that's very bad because you are introducing more electronic charge towards a negatively charged conjugate base center, and that will destabilize conjugate base and make it less acidic in that sense. Happy?
Yeah.
Cool. All right. So now, let's talk more about acidity. So I just talked about acidity is to do with the stability of the conjugate base. Yeah. So if you have a molecule such as, can you draw a carbon-carbon triple bond,
Okay.
and then have a hydrogen on each side? So this is a acetylene molecule, or you call it ethyne, because it's a carbon-carbon triple bond. It's the simplest ethyne molecule because it's just got two hydrogen. Yeah. Okay. And then can you draw next to it an ethane molecule? Ethane molecule and alkane with two carbon.
Okay.
So these two compounds, these two molecules, they are not very well known to be acidic.
Yeah.
But regardless of whether they are well known to be acidic or not, there are always things called super bases. Like we talked about a little bit about organometallic last week. So organometallic reagents are highly nucleophilic carbon.
Yep.
Full negative charge on the carbon. So that also means that organometallic reagents are very good bases. They are very strong bases. Some of them can be what you call a super base, like they can deprotonate anything, even things like whatever, one of these two. So one of these two can be deprotonated, trust me. But So actually, both of them can be deprotonated under certain conditions with specific bases. All right. Suppose we want to deprotonate with one particular base, but we want to know which one is more acidic. So you don't associate these molecules with being acidic. But I'm just asking you, between
Yeah.
an alkyne and an alkane, which one do you think is more acidic and why?
Okay.
So here you don't have a carboxylic acid group, but the same idea still applies.
Being acid means it loses a proton.
Yeah.
So if the alkene loses a proton, it will form CH3CH2 plus. And then since it has a CH3 group next to the carbocation, that means it would be stabilized. But then if we look at the
Sorry,
alkyne,
did you say carbocation?
yeah,
When you lose a proton, what is the charge on the conjugate base?
a negative charge.
Yeah, you're going back against your most basic principle here again. A proton is a H plus. When you lose a H plus, what's the counter charge? Conjugate base is always negatively charged because you lose a proton which is H plus. Unless you're talking about losing H minus, which it is no longer acting as acid. But we're talking about acidity here, relative acidity. So maybe you want to go back on your reasoning.
Yeah, the CH3 group would make it more unstable, the negative charge, because it pushes electron density towards the negatively charged carbon. And then for the alkyne, if it loses a hydrogen, again it'll be forming a negative charge. But triple bond, that means the carbon would have a lone pair. The negatively charged could be the lone pair could move to the other carbon by resonance.
Really? Show me. Uh, if you do that, then follow your arrow. If you do resonance doesn't work like that. Yeah, the electron has to hop around to the next atom. It doesn't linger around like that. So what you have drawn there is not a resonance form. You can't do that. Think about the triple bond there, carbon carbon. Do you want to kind of draw the orbital diagram for me? Do you know how the orbital diagram would look like when you have two pi bond?
Yeah. There's one pi bond above and below, and then the other one is sideways.
Yeah, okay. Show me on your diagram. Hello, can you hear me actually?
Yeah, I can.
Just give me a minute, yeah. Yep, that's fine. Yep. Can you hear me?
Yeah.
Why is this thing not working? Just give me a minute. My reference is very weird. Can you hear me?
Yep.
Can you hear me?
Yeah.
I can't hear you. It's okay. I don't want to use this. I'll just continue using. Okay, cool. Something is wrong with the AirPod. But anyway, yep. So the diagram is fine. But when you think about it, so what you have there is you would have your negative charge like that, right? Which is actually pointing because there is a sigma bond originally, and then the
Yeah.
negative is pointing along the molecule, whereas the pi bond is there. And if your negatively charged electron is in that along the sigma bond originally, it can't get delocalized into this pi bond, which doesn't make sense because they are not parallel to each other when you think about it. They are
Yeah.
pointing like to each other. So how can get delocalized if like that, right? So the negative
Yeah.
charge is still localized there. So when you think about it, what's the difference between a carbon-carbon triple bond and a carbon-carbon single bond? It actually comes down to this thing called percentage of S character. So we talk about hybridization when you form multiple bonds. So when you have a carbon-carbon triple bond there, what kind of hybridization do you have for that carbon there?
SP1.
So in a carbon sp1, and then you versus a carbon in the alkane. So what position when you have the alkane there?
SP3 for alkene.
Alkane, you mean? Yeah. And then when you have the sp versus the sp3 there, so you can tell that the percentage of s character is different between the sp and the sp3 because you have one s orbital and one p orbital mixed together versus you have one s orbital and three of the two orbitals of carbon hybridized together. So the percentage of S character is different there. So S character is good because S character is spherical. It distributes the charge better than the p orbital, which is just in certain direction. So it doesn't
Yeah.
distribute the charge totally. So having more S character will help you to distribute the negative charge on the conjugate base better. Yeah, that's
Yep.
the idea. So having S character is good, but here you have hybridization. So you need to decide which one has a greater amount of S character and how will you be able to justify that?
The alkyne has a larger S character
Like how
because
can you tell?
there's one S orbital and one P orbital
So
compared.
yeah, in that hybridization, in that sense, you actually have 50% S character in each of the orbital. Yeah.
Yeah.
Whereas in the alkane, what can you tell me?
You're combining one S orbital with three P orbitals.
So how many percent is that in terms of S character?
25% S.
Uh,
So
so you can tell which hybridized system will actually stabilize the negative charge better, and which one will give you a slightly stronger acid here. Do you get it?
yeah,
So what's a stronger acid, the alkyne or the alkane?
the alkyne, it has more S character, which means the negatively charge can be distributed more better than the sp3 one.
Yeah. In general, when you have an alkyne, when you have a carbon-carbon triple bond bonded to a H, you can deprogram that, not with your normal sodium hydroxide, but you use a organometallic base such as a butyl lithium.
Oh yeah,
So a butyl lithium is butyl minus and lithium plus. Very strong base because it wants to go back to being butane. So it will
yeah,
take away the H plus from there and then it will release butane, right? And then what you will get is you will get the conjugate base with a Li plus, which is very unstable also. It will react as a nucleophile now. And that's how you can form new carbon-carbon bond because previously all you thought about was just nucleophile attack carbon, nucleophile attack carbon. But
yeah,
we talk about it when you can reverse the polarity on the carbon by making it nucleophilic with the use of metals because of the difference in electronegativity. The metals will be the one carrying the positive charge, leaving you the nucleophilic carbon source. Okay,
yeah,
happy?
yep.
Cool. Next one is can you draw for me nitrobenzene?
Nitrobenzene. Yes. Okay.
Okay, and then on actually draw two of them. So one nitrobenzene and then the other one also another nitrobenzene. Um, and then on one of them, draw a NH2 at meta position, and then NH2, and then the other one draw it at a para position.
All right, done.
Okay, can you show me your two diagram? Yeah, okay, cool. So one of them is I don't know, um, 3-nitrophenylamine. The other one is a 4-nitrophenylamine. Okay, cool.
Yeah.
So going the other way now. So we're talking about relative basicity of phenylamines. So as you know,
Yeah.
phenylamines are slightly less basic than ammonia. And ammonia is already a weak base, but phenylamines are slightly less acidic than ammonia, which you learn in N levels. But anyway, between these two, how would you decide which one is a stronger base, which one is a weaker base, and why?
The basicity depends on the electron density on the lone pair
Of one?
of the amine, the NH2 group.
Yeah.
NO2 is an electron withdrawing group.
Mm-hmm.
And NH2 is electron donating activating ring it activates the ring. And NH2 activates the ring at the ortho-para positions.
Is there a reason why you're talking about activating the ring? We're talking about basicity here. We are not talking about reactivity towards electrophiles. Reactivity towards electrophile would mean electrophilic substitution on the ring, but basicity is to do with the nitrogen on the phenylamine, not the benzene. When the
Okay.
benzene ring gains a proton, that is not basicity anymore. That is basically you're pumping the electron density into the ring and you're taking in a H plus, which is electrophilic substitution already, or electrophilic whatever reaction it is. So we are no longer talking about that. So your idea on the activating position thing, it's kind of on the wrong track here. So maybe you want to rethink your strategy.
Yeah. For NO2 electron withdrawing group, if I draw the possible resonance structures for NO2, then nitrogen has plus, oxygen has minus, and then so NO2 makes the ortho and para positions are the electron deficient position. So that means if NH2 were connected in the para position,
What do you mean connected?
bonded to if NH2 were bonded to the para position, bonded to, that means, wait, the lone, because the carbon at the ortho position, ortho and para positions are electron deficient. So the lone pair in the nitrogen group for the para amine would be more likely to share electron density with the carbon. So that means the lone pair is less available compared to the meta one, which the nitro group makes the carbon at the meta position more negatively charged, so the nitrogen would be more negatively charged. I mean, more higher electron density on the nitrogen for the meta group position. So it would be the 3-nitrophenylamine group, which is more basic.
Sorry, which one is more basic? Do you want to show me a diagram? Because I can't really just follow your reason. Okay. Leave it a little bit higher again. So based on what you just told me, everything, and you said that one is more basic because you talk about something about the chemistry. You think you'll be able to show on the diagram what you actually just told me?
Yeah.
I thought you were actually scribbling stuff on your thing, but it turns out that you were just circling things. Anyway, just keep on drawing.
Nitro N double bond O. Single bond O has a negative charge. NH2 lone pair.
And you said you think the para one is more basic. Am I correct?
Or
You said the para one is more basic, right?
the meta one.
Oh, sorry, the meta one is more basic, right? Okay.
Yeah.
Got anything for me?
Yeah. This structure. Oh. But then this one is not really possible because of the 5 bond.
Oh, okay. So with the meta one, you can't. No, your one on the right is already wrong. Okay. So what you're saying is, if you have that, if you have the meta position, if you try to do your arrow pushing like that, so you can see that from the cocoon structure. I can't,
Yeah.
I can't delocalize the last one into the nitro group. I can't. No matter how hard I try, I can't. To make you see what is happening is, I can put a negative charge on that carbon instead, and then I can think
Yeah.
about, wait, hang on, that negative charge is not gonna go anywhere. It is not it's not overlapping with the NO2 group in there at all. You can't do that. Try it for the para one. Try to draw if you can get it for the para.
Okay.
So we established that with the meta, no matter how hard you try, you can't get there, yeah?
Yeah. Lone pair goes to
Can you count how many covalent bond the nitrogen on the right has?
S 5.
5, and you still have you forgot the charge on the O minus, and you forgot the charge on the NH2, which is now 4 covalent bond. There should be a plus. So maintaining charge is something you need to keep an eye out for. Yeah? When you push your arrow around and the nitrogen now has 4 covalent bond, you need to have a plus on the NH2 plus, and you will have O minus on the one up there because it's still a single covalent bond, the oxygen. But anyway, now you have a nitrogen with 5 covalent bond. Can you tell me why nitrogen cannot have 5 covalent bond? What is wrong? Nitrogen cannot form 5 covalent bond. The maximum number of covalent bond that nitrogen can form is 4. Why?
Nitrogen has 1s, 2s orbital, 2p orbitals. So if they were to hybridize, then maximum hybridized orbital you can get is 4.
Between 1 and 1.
1s orbit, 2s orbital and 2p orbitals to form.
Yeah. So the 1s is not involved in bonding, yeah, because the inner shell electrons, they are held much more tightly. They're just chemistry is to do with electrons, to do with the outer shell stuff. Anything to do with inner shell stuff will be a physics thing already, nuclear chemistry, okay? But if you want to go into the inner shell, that is quite difficult chemistry because the outer one is held less tightly because of all that weaker effective nuclear shell. So obviously the chemistry revolves around the outer shell, which in this case is the 2s and the 2p. Maximum you can have in 2s is 2. Maximum you can have in 2p is 6. You don't have the d orbitals when you are, well, you actually have empty d orbitals, but those are quite high up in energy to be accessible at all. So yeah. I mean, it's just using the 2s and 2p. Maximum is 4 covalent bond. You cannot have a structure that looks like that with 5 covalent bond. Yeah? Nitrogen does not do that. So can you correct your diagram and see if you can give me a correct diagram?
Listen.
Yep, okay. Can you go one more step? Do you think you can delocalize the negative charge into the nitro group?
Delocalize the minus charge into
the nitro group. Can you or can you not? That's the question.
Well, yeah, if the double bond and double bond or the electron from the double bond enter the oxygen, then the lone pair could enter it, then you'd form the resonance.
Show me what you mean.
Yeah.
That is correct, but the order of you doing thing is actually wrong. So it's not the nitrogen, it's fine. That one is correct. That's the correct resonance structure. But the order of you doing thing is wrong. You were saying that the nitrogen oxygen double bond will break first, then that negative charge can go in and form that. No. The arrow pushing goes wrong. The negative charge goes and form that double bond between the carbon and the nitrogen. And then because of that, the nitrogen cannot have 5 covalent bond. Because of that, then the nitrogen oxygen double bond breaks and it becomes a negative charge on the oxygen. So that's the order of things, not the order you mentioned, right? Although the conclusion is the same, you get the same resonance structure. So based on all this, we have just shown that the nitrogen lone pair on the phenylamine can get delocalized into the pi system, and because the NO2 group itself is trigonal planar as well, so it's actually planar because it's sp2 hybridized, is planar as well with the benzene ring. So essentially, even though the NH2 is slightly bent because it's 107 instead of perfect 120 degree, because phenylamine 3 bond pair, 1 lone pair, but somehow it can delocalize the lone pair to the ring, and it can delocalize these. Both of them will have the lone pair delocalized to the benzene ring. But when the nitro group is at position 4, as you have drawn, you can further delocalize the negative charge into the nitro group. And what does the nitro group do? Because it's an electron withdrawing group by a resonance effect. In fact, you have just drawn the resonance structure because you have done electron withdrawing by resonance effect. And electron withdrawing by resonance effect is going to be stronger than electron withdrawing by inductive effect, which is the best you could get with
for
the meta position.
meta.
Yeah, because the meta position you can't delocalize into it, but the NO2 is still withdrawing regardless. So the resonance will always be a stronger effect, and therefore the lone pair is less available to take in the H plus for which position?
Less available to take the H plus for the meta position. I mean the para position, because the lone pair is in the nitro group.
Yeah, it can delocalize away into the nitro group as well. Yeah. Okay. So if I put in some phenylamine, if I ask you to rank them, so if I have phenylamine and then nitrophenylamine in meta, nitrophenylamine in para, so where does phenylamine rank? Is it most acidic or least acidic? Sorry, most basic or least basic?
Which one? The para?
Phenylamine. If I put in one more, phenylamine, just phenylamine without
phenylamine.
without any nitro group.
The meta one is more basic than the phenylamine one, and then the para.
Because
for the the non-pair cannot be delocalized into the ring that much. But then wait, there's no, never mind.
For which one? Sorry, what are you saying again? So shouldn't you be thinking before you say anything? Shouldn't you be thinking deeper? There's a reason why these questions are being asked, because once you get one correct, you will get asked another one. If you get stuck on one, you will be stuck there. So that's how it goes. There will usually be in order of increasing difficulty, and then having two choices. And then once you think you sort that out, they'll introduce a third variable. In this case, phenylamine. So where does phenylamine rank then? Is phenylamine most basic or least basic or somewhere in between?
Phenylamine is bonded to phenyl ring, but then for the
all of them have a phenyl ring. You see, all of them have that's why it's called phenyl ring. Because the only difference is no nitro group has nitro group. Has nitro group in position versus in para position. That was what we've been talking about for the last 10 minutes. Now the new question is, where does phenylamine rank in terms of basicity?
The nitro group is an electron withdrawing group. Also, it's also a withdrawing group.
Yeah.
So, since phenylamine has only the benzene ring,
yeah,
and compared to the nitrophenylamine, which has nitro group, so that means phenylamine should be the most basic because it's the lone pair is the most available.
Yeah, that's right. Because when you just have phenylamine, we already established that when you have the para, there's the most electron withdrawing. That's by resonance. But when you're at meta, you can't do the resonance electron withdrawing. But regardless, you still have the electron withdrawing group by inductive effect. And in that case, when you have an electron withdrawing group by inductive effect, it's still electron withdrawing. You can withdraw the electron density from the amines because the phenylamine actually delocalizes the lone pair into the ring at some point. So you can, whatever we show just now, like that structure there on the so the one that cannot get delocalized, but the NO2 can still inductively electron withdrawing and kind of still make that slightly favored, although it's not going to be well stabilized, but it's going to be better than just for phenylamine on its own. So phenylamine is the most basic. Cool. All right, let's do some synthesis. Can you draw for me a phenol? Sorry, not a phenol. Which one I'm talking about? Oh yeah, can you draw for me a phenol? Yeah. Then at the para position, draw for me a NH.
NH2.
Actually, I just show you this thing. NH.
Okay.
And then CH3. C double bond or CH3. You get the structure?
Yeah.
Can you tell me how you can make this from phenol?
Okay. From phenol. Uh, let's see. There is liquid from phenol. Ah, the NH is in the meta position. Phenol. And
Uh, what are you,
well,
yeah, what are you thinking?
we would need the electrophile. Well, from phenol, we probably would go to the phenol with the NH2 group, and then from there we could
Wanna show me your reaction route? I mean, before we talk about agents and conditions, so you're saying that that one goes to that. Um, Back to the original structure. You got it at the wrong position. We want it. We want at the para position. Sorry, you got the. Just change the phenol. Then you can get it. Um, yeah, it's the para position. So just change the OH to the para.
change the OH to para position. Sorry.
So basically, they are para to each other. Yeah. Then you can tell me.
That means this needs to happen first. So to get this is the first step, but then to get from phenol to the phenol,
Doesn't matter, whatever that is. Yeah.
we need to we need to add a nitro group. Then
That's
from the nitro,
that's
from the
called
nitro,
aminophenol, by the way. It's a aminophenol because it's an
yeah,
aminophenol. Anyway, yeah.
we need to get from the phenol to nitrophenol and then aminophenol. So from phenol to nitrophenol just needs to dilute and nitric acid HNO3. If it was concentrated, then the nitric it would form it will try substitutes, but then if you use dilute, it will monosubstitute. And then we don't need a catalyst because phenol is activating. And then from the nitro group to reduce it to the NH2 group, we need to do another two steps process. We need to add 10 plus concentrated HCl, followed by reflux. And then the
What
second
does
step,
that do? What does that do?
the 10,
Yeah.
it's a reducing agent. So that would form 10 reducing agent concentrated HCl is, let's see, NO2. Being a reducing agent, it would oxidize. So that means tin would lose its electrons. And then HCl is a proton donator. Huh.
It's all right. Want to show me what you've done?
I haven't drawn much yet actually, but
Oh, it's all right. Doesn't matter. Yeah, it's fine. Yeah, okay. So you're saying that. Show me your scheme again. So like, what are the steps that you would take? So the most important thing in organic synthesis is, so you've done the nitration and then you form the amino phenol. So what next to go to your target? Like, what else would you do?
from here.
From the amino phenol.
There's a from the amine, there's now a amide group which is being formed. So to do that, we would need an acyl chloride. So probably that's 2 carbons. So ethanoyl chloride to form.
Okay, nice. You don't need to write. So everything.
Uh,
Okay. The the product that you just is paracetamol, Panadol actually. Okay, cool. There are a few questions that come up. So first of all, why did you say if you use concentrated nitric acid, it will go to trinitration or dinitration? Basically, the question is why do you use dilute nitric acid? Why?
dilute nitric acid.
Yeah, you were saying like if you use concentrated nitric acid, you will get multiple nitration. Yeah.
Yeah.
The question is why?
Why? Because there's more. Because with the if we were to use dilute acid, dilute acid, it could not further substitute because nitro group actually uh, deactivating the ring, which makes it susceptible to a new electrophil substitution.
Oh my God, you're chopping up. Well, anyway, so your idea is on the right track. So corn nitrate will oh, show me. Show me what you've drawn there. Have you drawn anything? Oh, okay, that's
This
fine.
one
So
deactivates the ring.
so you're saying that it goes straight away to the para position. Is there a reason why you're not forming the auto?
Oh no, it forms both ortho and para, just 50-50 yield.
Oh, 50-50. Okay. Let's talk about maths. Okay, let's talk about maths now. You say 50-50. What makes you say 50-50?
Right.
Is there why you say 50-50?
Because then either ortho or para, but then there are there's two ortho positions that would give the same thing. So it should be wait, there you go. They could form this, and this, but then this would be 1 and thirds, 1 and thirds, 1 and thirds.
Mm-hmm.
But then these two are ortho positions. They're considered ortho positions.
Yeah.
So it should be 2/3 ortho position, 1/3 para position.
So there's around 66% auto isomer, 33% para isomer, right? Okay, what I'm about to tell you is you get very little of the para isomer, maybe like 10% only. The rest of it are auto isomers. Suggest why.
So that's why I think just by looking at it, it can, since the nitro group is closer to the OH group, then it can form the intramolecular hydrogen bonding, which makes it more favorable to form.
Yep. So it's essentially like quite a stable thing to form. Whereas the other one, yeah, it's further away, but you don't get that, right?
Oh,
Can you see that?
yeah.
You see this? If you draw the intramolecular thing again, yeah, you can only see it if you get the O minus on the one side because the nitrogen oxygen double bond is already tied up. So the O minus, you have a carbon nitrogen single bond that can rotate around. So the O minus are essentially
Yeah.
delocalized. It's not just on one side O minus. It's actually delocalized over the nitrate anion anyway. Okay, so the idea is that but yeah, so the para isomer yield is actually quite low, but it doesn't mean that you don't get it. You still get it. Okay, cool. The idea of using the versus the concentrator, you kind of got the right idea that NO2 is deactivating. So once you have one NO2 group on the auto, it doesn't go further, unlikely to go further, unless you have concentrated. But the other thing is that you don't want to use concentrators because phenol is quite highly activated already. So you should know that phenol can react with aqueous bromine straight away as well to give you that white
Yeah.
PPT.
Tribromo.
Phenol. That's just like the long term delocalize itself pretty well into the ring, and it kind of activates the whole ring to any electrophile. That's why electrophilic substitution on the benzene ring of phenol is actually quite prominent. Yeah. Okay, cool. So your next argument is you do reduction. I have no question on that. Do reduction with tin, con HCl. You could do it with zinc and HCl as well. Any reducing agent will do. So these two are the cheap ones. But there's also a reason why tin doesn't is not favored that well. Partly because tin compounds are quite toxic actually. So you might have heard that somewhere, but you should read out like tin compound. Anything to do with tin are quite bad. They are highly toxic. So sometimes zinc is the preferred reducing agent, zinc HCl.
Oh,
Um, but the next step, I know A level always use tin, but actually like tin chemistry is very toxic, very very toxic.
yeah.
Especially if you are doing Panadol, human consumption. Don't want any traces of tin in your Panadol at all.
Yeah,
It's yeah,
definitely.
human consumption. Yeah, okay. Anyway, so onto the final step, you use acyl chloride with the amine. Why did you choose acyl chloride?
Rather than the ethanoic acid.
Yeah,
If acyl chloride, carboxylic acid would form a equilibrium mixture with it'll form the equilibrium mixture, so the yield is not 100%. But then for the acyl chloride, the yield is 100% because acyl chlorides are more reactive. The
but you say acyl chloride is so reactive, right? Yes, amines will react with it, no problem. Can the phenol react with acyl chloride?
yeah, it can
Eh,
also.
do we want the phenol to react with acyl chloride to form
No,
our paracetamol? Eh,
no,
it's so reactive. Oh, it's too reactive. I can't control it. I can't stop it just at the amines. What
yeah,
should
for
I
sure.
do? Do I want a super reactive one?
No,
What can I do?
so concentrated ethanoic acid then.
Uh, eternal access is still not a good thing to use because what you have is it can form ester as well with the well hang on Corn ethanol acid. Yeah, ethanol acid can work. Yep. Because like without the corn sulfuric acid as a dehydrating agent, you're not promoting the acidification. So yeah, corn ethanol acid on its own is okay, but without any sulfuric acid at all, because otherwise promoting you'll be promoting dehydration, and corn ethanol acid shouldn't be that good of a dehydrating agent, so it should be okay. But at some stage, you are bound to get a little bit of acidification as well with that. But actually, they use in industrial. If you look up Panadol synthesis or paracetamol synthesis, in industry they actually use something called anhydride. Have you heard of anhydride?
Anhydride.
Yeah, acid anhydride. So it's like oxygen in the middle, and then it's bond C double bond O on both sides.
C double bond O.
So it's like
Oh.
it's a less reactive version of carboxylic acid. So you will use things like ethanoic anhydride, which is that. Oops, sorry. Can you see?
Ah.
Yeah.
Yeah.
And the reaction might take longer. It's more reactive than SR, so it's somewhere in between. And you can tailor, and it's not reactive towards the phenol. It's amine itself will be okay. Cool. And then suppose if I have a normal amine. So I'm not talking about this particular amine because I'm not going to use acyl chloride on this final step. Yeah. Suppose I just have a normal amine. Call it R and H2. R and H2. Just any amine. Yeah. Okay. Just something with an amine. And then I'm not even talking about phenylamine. Okay. And then it can react with acyl chloride, such as ethanol chloride, for example, CH3COCl. Can you draw me the mechanism this reaction?
Yeah.
Can you?
Mechanism. Okay. Since looking at the ethanol chloride, the oxygen and chlorine group polarizes the carbon, so it's more positive.
More delta positive.
Yeah.
It's not positive, it's delta positive.
More delta positive. Which means the lone pair and the primary amine can just attack the positively charged nucleophilic substitution, and then it forms the C connected to CH3 connected to oxygen.
If you got it drawn out, just show me the drawing. It'll be a lot easier.
Oh yeah, no double bond. Yeah.
Oh yeah, if you say no double bond, that oxygen is a single bond. That also means if oxygen is a single bond, it has an O minus, which means you are also missing another step on your first mechanism. You're missing one more step because you forgot to break the C double bond off. So once the nucleophile attacks it, that carbon cannot form 5 bond. That's why you said no double bond, because you're supposed to push the arrow up to the oxygen, and that's how the oxy anion intermediate is formed. Yeah?
Yeah.
Okay. Continue.
So I'm just redrawing actually because one is confusing. And then like the lone pair from the oxygen forms a double bond with the carbon, and then which
Show me a mechanism.
kicks out the Cl.
Yep, that's fine. That's done. Cool. So that one is done. That one is all right. So in reality, this is a condensation reaction because if you had started with the carboxylic acid, you have kicked out a water molecule at some stage. Yeah. And that's why it's called a condensation reaction. For every one amide bond form, you will kick out one water molecule. If you form a bis amide or amide ester, you will kick out the appropriate number of water molecules. Okay, cool. That mechanism is easy. Nucleophilic addition and then eliminate something. Overall, it's a condensation. Okay, just two final questions. This is a target molecule. You see that? There's a benzene ring.
Benzene ring.
There is a CO2H. And then there's a bromine para to the CO2H. And then there's an NO2. Can you make this from methyl benzene?
Methyl benzene.
So I don't need you to write down all the reagent and stuff, but you're supposed to tell me like how are you gonna make it like in, you know.
Okay.
Any idea?
CH3 and COH are both electron activating, so that means it doesn't matter if I oxidize it early.
Sorry, did you say CH3 is activating?
CH3
Yeah.
and COH, because
Activating.
CH3 is deactivating, I think. Right.
And CH3 is deactivating or activating?
Well,
So if you have benzene,
plus.
you have benzene versus methyl benzene. Which one reacts under harsher condition? Which one reacts under milder condition? There's a slight difference in reactivity with electrophiles between benzene and methyl benzene.
Methyl benzene, the carbon is delta plus, right? And then, wait, no. Carbon is more electronegative than hydrogen. So
what are you talking about? The CH3 itself is activating, but not so strong because it's just inductively electron donating. So so for benzene, for electrophilic substitution with benzene, you will need to heat up quite badly, like up to the boiling point of benzene, which is like 60, 70 degree. Whereas if you have methyl benzene, you can do it at 40, 50 degrees Celsius, which is well below the 60, 70 required if you react benzene with electrophiles on. Okay. And CO2H is not activating. CO2H is deactivating. Is CO2H activating? No. Why? Because that carbon does not have a lone pair to donate into the ring. Therefore, it doesn't do resonance donation into the ring. It doesn't activate the ring by resonance. Does it do electron withdrawing by inductive? Oh yes, it does. It's got two very highly electronegative oxygen. It's only electron withdrawing by inductive. It cannot donate into the ring. No, there's no lone pair on the carbon. If you draw out the structure, you can see there's no lone pair on the carbon or carboxylic acid. So carboxylic acid is not activating. Is deactivating actually. Okay. You wanna rethink your strategy? I stopped you there because your first strategy was wrong already.
that means CH3 and activating group, so that means it directs electrophiles at the atom and para positions, compared to COH, which would deactivate the ring. So it would direct electrophiles at the meta position.
Do you get the question? The question is this, yeah? So this is the target. Your target is this, and you are to start from methyl benzene. You start from methyl benzene to this. Okay? Cool. So in other words, I could ask you this question. Which step do you do first? What do you want to do first? That's the other question that I can ask you. Rather than just make this. What should you do first?
We should add the bromine to the para position first. Because
why?
Once we oxidize the CH3, the COH would make the ring less reactive susceptible to electrophiles.
Okay. All right.
So, but then
So,
we only want a mono substitution.
okay.
But
We are bound to get isomer, by the way. We are bound to get the auto and the para isomer. There's no way around it. You cannot, because there's no other interaction here. And I won't be able to tell at what percentage it is, but you're bound to get auto and the para bromine methyl benzene isomer. What you can do is, what we'll do in the lab is we'll distill them up because they have different boiling point, different positions, right? Even they are isomers, structural isomers. So, but then because of their different position, they are packed slightly differently, different intermolecular force, slightly different boiling point. How do you separate things with different boiling point? Fractional distillation. You can separate them. You can tell their difference with, you can't tell it by mass spec, but you can separate them by distillation, and then you can get an NMR of them because there'll be difference. Yeah, I won't talk about NMR right now, but as you can see, if the bromine is para position to the methyl, they are symmetrical.
yeah,
The NMR will be simpler. It will be simpler in the aromatic region than if it is at the auto position. So if you get two things out, it's very easy to tell which one is auto, which one is para. But you could also get a third thing, which is a bis brominated, or even a third thing, tris brominated, basically multi-substituted thing. But the more bromine you have, potentially you can increase the boiling point already. So if you're collecting every single thing, then that's fine. But anyway, so after you get the bromine at the para position, so suppose that is the stuff that you already distill out. So how would you proceed next?
Oxidize the methyl group to carboxylic acid. And then, since the carboxylic acid group directs electrophiles towards the metal position, you could do nitration.
Okay.
Dilute.
I agree with you on that strategy. So yeah, you do bromination first, and then you oxidize the methyl chain, the methyl benzene to carboxylic acid, and then you do nitration. That's the correct strategy. But the way you explain the final step, the nitration, is you were fixated on saying the CO2H is electron withdrawing, and then it directs to the metal position. But when you are electron withdrawing, when you are directing groups also, you are essentially a deactivating group already. That means your directing effect is actually quite weak, right? In this case, you have to use corn nitric and corn sulfuric acid as a mixture, which give you the source of NO2 plus anyway, right? So the CO2H is not the important thing there, but it is a good factor there because it's being held by the other group, which is a bromine. What does the bromine do? What kind of activating effect does it have? Does it activate or does it deactivate?
It activates
The
because
ring.
the lone pair can be the locally
Exactly,
served.
right. So even though it's electronegative by inductive effect, but then it resonates into the ring because the lone pair can get the localization in the ring by resonance effect. And in a way, it's actually activate the auto position quite well. Yeah. Of course, the para position is blocked by the carboxylic acid there. And because the bromine there, there's activating has a stronger effect than the deactivating group. Although the activating will direct it to metal position, but you should be thinking about which one is, the one which is activating, it's being helped by the CO2H being CO2H first, rather than it being CH3. Okay, so that should be your argument for it, really. Okay, I actually have one final question for you. Can you balance a chemical equation? If you have a you talk about reduction of nitro group just now, right? Reduction of nitro group. Happy? Okay, cool. So suppose like I'm doing this reduction, I'm using zinc. So zinc as a reducing agent. So zinc will be oxidized. Do you agree?
Yeah, correct.
What do you think the zinc will go to? What do you think the zinc metal will go to?
Where does
You want to write me the half equation for what you think the zinc will become when it acts as a reducing agent? So zinc 0, right? Because it's a zinc metal.
Yeah.
Trust me, this is the last one. Balancing equation.
Things with reactor. Oh, half equation.
Yeah, half equation. Just what will happen to the zinc? So just the zinc.
Lose 2 electrons at Zn to form stable ion Zn2 plus.
Just show me your half equation. Then I can tell whether. Yeah, that's fine. Yeah, the zinc reducing agent get oxidized, right?
Yeah.
And for losers, it's electron. Zinc 2 plus is a very common oxidation state. It doesn't go to zinc plus because, I don't want to mention the reason, but, it likes being zinc 2 plus. Yeah, okay. As far as you know, the zinc 2 plus is happy being on. So it doesn't go to zinc 3 plus or whatever. All you have to need is zinc 2 plus. Okay. Now you have a nitro group. So make it simple. Make it RNO2. So R is just R, whatever group it is. So the R doesn't change, right? It's just a carbon-based backbone. RNO2. What does it become again when you reduce nitro group? What does it become?
It becomes amine RNH.
Yep, so the R doesn't change, then you get RNH2. So you're doing reduction. So this reduction is done in the presence of a metal and an acid, right?
Yeah.
So can you write me the other half equation for what happened to the nitro group? Do you get the question?
Yeah.
So RNO2 become RNH2. So the half equation for that.
Okay.
Please don't use the square bracket H square bracket O, okay? That doesn't work in a half equation. That works in an organic full equation. That does not work in a half equation. In a half equation, you should have electrons and something else charge.
Oh, NO2. Nitrogen is oxidation states. NO2 is +1, and then NH2 minus -3. So that means that's oxidation states.
So you're trying to balance this equation with changes in oxidation number, which is actually not a bad thing to do if you have metals. If you have non-metals, it's difficult and it doesn't make sense. Trust me, it does. With metals, it makes sense. With metals, it's easy, like the manganate 7 and the chromium, the dichromus 6 we talked about last week, perfectly making sense with that. Okay. When you have non-metals, there's an easy trick. Okay. This thing is done always. You need to think: is it in acidic condition or is it in basic condition? If in basic condition, you should have OH minus and H2O lying around, because you can have alkaline fuel cells, fuel cells. Then you need to use the right equation, right? But this equation, this reduction is done in presence of an acid, as you know it, tin con HCl or zinc con HCl. You're doing it in the present acid. In the present acid, you have H plus, you have H2O. So you can always balance this kind of equation with H plus and H2O. The question is, which side is which side? And it's a reduction. A reduction means it's a gain in electron. So it's a half equation. So you must know where to put the electron. The electron must be on the correct side because you must gain electron. Okay. The other thing is electrons are negative, but electron group has overall no charge, and your amine group has overall no charge. So now you have electrons. You're adding electrons on one side, but electrons are charged. Electrons are negatively charged. How can I balance the charges in a half equation when I know what kind of medium it is in? Is it acidic? Is it basic? And then obviously when you are acidic or basic, you have water lying around. So play around with it and see if you can balance this half equation.
The H plus and the electrons must be in the same side of the.
Okay.
And then the H plus must be with the NO2.
Okay.
You want to form NH2.
Yeah, you want to do reduction, yeah.
And so that means water is in the product side.
Yeah. Okay.
So to balance, there should be 2 H2O that balances the oxygen. And then now there's 6 hydrogens on the product side. So that means we need 6 H plus on the reactant side. And to balance the charge, we need 6 electrons.
Done. And once you get this half equation, you can balance it with the metal bit very easily, right? Okay.
Yeah.
So these are the kind of redox equations that might come out in A level as well, by the way. Okay, but obviously, like in the normal organic sense, they usually ask you to use the square H or the square bracket oxygen to denote the reducing agent or the oxidizing agent. But again, you can try this with the tolerance reagent reactions. The tolerance reagent is basically silver 1 becomes silver 0 because you're forming silver mirror. And then the aldehyde become, aldehyde become, what does the aldehyde become? What does the aldehyde become? Sorry? And that is wrong because you are in a basic medium. A tolerance reagent is in the basic medium, it's in sodium hydroxide. Look it up, and therefore you're essentially forming a carboxylate salt. So if you, so you have an OH minus and H2O instead of H plus and H2O. That's the kind of redox equation that can come out in organic chem as well. Yeah, cool. We'll leave it there for today. So we started off by talking about acidity and basicity. It's very important to draw out structures and things like that. We talk about synthesis, where strategies are very important, and the use of reagents. The use of reagents are very important because you need to decide the reactivity. Just because you want to focus on one side of the reactivity, you cannot ignore the other side of the reactivity without explaining how or why. You can say you can get other isomer, but you can distill this. But things like the phenol and the amine, acyl chloride is too reactive. Definitely will react with the phenol and the thing. In fact, these are the kind of questions that usually come out in paper 4 as well because it's a tricky question.
Yeah.
And then things like that. And then strategy wise, it's activating effect on the benzene ring, how reactive it is, and position wise, like which is more important, inductive or resonance. Everything has a role to play. Yeah? So sometimes they started with 2 or 3 things, and then they throw more things into the ring. That's how they distinguish candidates. Okay, that's all for today. But have you finished your personal statement yet?
Yeah.
Has anyone read it at all?
Yeah,
Have you given it to not just friends, give it to a couple of tutors as well, so that they can give you feedback. I'm not saying like they will give you feedback. I'm not saying they can improve whatever you have already, but the more feedback you get, the better it is. Your friends might not have seen personal statement before.
Yeah.
Tutors would have more experience with seeing personal statements, and they might be able to give you a few pointers here and there. And even though I said like the TSA is more important for you than your brother, because your brother only has the personal statement for them to decide. Personal statement and school reference and previous exam result to decide whether you get interviewed. For you, it will be like interviews, and then the past exam result should be no problem. The forecast grade should be no problem. School reference should be okay, but you should and then personal statement might not be a big thing, but it might also be a big thing for you as well. So it's good to have like the best statement you can think out there by yourself. How's the TSA preparation? Like, have you given and see if you can do them?
Yeah, I went through the syllabus already. And
oh, okay. Have you gone through 1 or 2 papers and did they seem alright to you? Like, are they doable?
I did the 2014 one.
Is it doable or?
Yeah, I mean,
did you?
It was simple, kind of. Some of them were tricky.
I know. Like you say, it's simple. You could do it. Did you check your answers and did you compare the answer key whether you get most of them correct or not?
Not yet, actually.
You won't be able to tell whether you got them correct or not unless you check. Yeah, you cannot be that kind of super cocky confident whatever you call it. But you need to check to know where you went wrong. And correction is the most important thing, like to understand where you went wrong. To get all of them wrong is okay at this stage, but to understand where you went wrong, it's very important for you not to repeat that kind of mistakes. Things like hydrogen bond, negative charge and negative charge. Things like nitrogen with 5 covalent bonds, for example.
Yeah.
Things like, I don't know, think about it before you want to say something. And you might know it, but sometimes slip out of your mind. So do correct yourself when you notice it before someone else notify you. Okay. There's a reason why something is being asked in an interview. There's a reason. There's a reason for everything. Okay. So they might want to know you. They might want to test you. I don't know. Okay. But I'm quite confident you'll get an interview in December. Usually they'll send out the thing in November saying like, do you want a Skype interview? Then you will say yes. Unless you want to
Yeah.
fly to the UK is also up to you. But yeah, I mean, if you do decide to fly to the UK, you get to stay 3 days in Oxford for free. Uh, Cambridge doesn't do lodging at all for applicants, but if you get interviewed at Oxford, you get to stay there for free for 3 days. But obviously, you pay for all your flight and.
Yeah.
Okay, cool. I'll leave it there, and then yeah, maybe just recap all your A level stuff. Next time we talk, it won't be on organic anymore. We'll be talking more on physical chem again, physical chem and
Okay.
maths. Okay, I think that's enough organic already. Cool. All right.
Yeah.
Bye.
Okay.
I'll stop
Thank you, sir.
recording.